Today's our class is going to be based on three different factors. Number one, we are going to be touching on series circuits. Number two, that fancy circuit that I gave you uh, for parallel circuits, we're going to get into that as well, which is this circuit here. Also, we are going to solve this together, and then we're going to cover as well combination circuits. Okay, so first of all, to get into this circuit here, what we are going to do is that pretty quickly, I'm going to show you how to draw a circuit like that using Falstaff. I'll go to Falstaff and I'm going to share my I'm going to share my screen with you. Okay, like right there, we got Falstaff. So all we have to do, okay, I can delete the whole thing, and all we have to do is just go here into draw, and then we are going to draw like some of all these different components. Like if we just hover over each one of these labels, then we can start adding all the different components. Okay, so the first component that we are going to be adding in this case is going to be our power source. Okay. So I'm going to be adding a voltage source with two terminals. So, okay, so it's going to be DC, of course. And then, like if we look at the drawing that we have, we are supposed to be using 4 resistors that are connected in parallel, and that it looks like if they are connected in parallel. So now we are going to add 4 different resistors. Okay, something else that I want to do in this case is that I'm going to use switches. Okay, so we are going to be using like 5. Okay, so first I'm going to be adding the switches because also we are going to be using 5 ammeters. So let's add the switches first. There's one switch here, and there is another switch that comes right here. Okay. Gonna press K. Gonna grab the switch here and just put it there. Okay, so now let's add our meters. So A1, which is the total power. There, I found it, a meter. Okay, so I added this ammeter like with the current going in that direction. So I want to do the opposite. Well, actually, I'm gonna do this. Swap the terminals. So now we can see that the current is gonna go in that direction. Okay, and even when you're drawing, this is the negative terminal here, and that's the positive terminal. I said last week that it doesn't really matter if we are using for these circuits, it doesn't matter if we are using the electron flow theory or the conventional flow theory. With the simulation software, we have to use the conventional flow theory because that's the way the software was set up, because it's mainly used for electronics. So let's finish adding everything else. All I have to do now, instead of going here to the draw section, I just copy and paste. In my case, I'm just gonna say duplicate. And then I can get another meter that we are gonna be placing right here on the top. I'm gonna grab it. So, and then I'm gonna duplicate this meter now. Okay. So, and this is gonna be A3. And then I'm gonna get another meter that we are gonna call A4. Okay, and the last one is another meter that we are going to duplicate that we are going to place right on the top here, and we are going to call A5. So all we have to do left, all we got left is just to make the connection. So I'm just gonna add wires. Just connecting all the different points. And now this is the same circuit that we have in the handout that I gave you. Like this is the same circuit that we have in this handout that I gave you like a few days ago. Okay, so all what we have to do now is just to get the different values, 25, 52, 104, and 50. So let me do that now. Let's change the values because everything by default is 1,000. I'm gonna open, like, I'm just gonna change these values. So I'm gonna stop the simulation, double click, and change the value. Just type 25. This one, 52. This one, 104. And the last one, 50 ohms. Okay, so now I have built the very same circuit using Falstad, the very same circuit that I gave you for simulation. And the reason why I'm showing this to you this morning is because you are going to be getting into a lot of different combination circuits going forward. So this is going to be a very handy tool. So whenever you are stuck, whenever you are not sure how is it that your current flows, you are going to come back here to Falstad. I'm going to be posting this page in such a way that you can modify it. So you can always go back to this page and once more refresh your memory. Okay, I'm going to change the speed of the current. And you can see how these yellow dots that represent the current, how everything is flowing. Okay, so that way you are gonna be able to do any simulation that you want, and you are gonna be able to solve and find the values for any given circuit. It doesn't really matter how difficult it looks. This will, I mean, it has the capacity of building very, very complex circuits. So it is impossible for me to give you a circuit so complex that you wouldn't be able to build it using Falstad. Okay, Falstad, it would be way, way more advanced than anything we can study in this course. So always make sure, anyways, that you adjust speed current, that way you are going to be able to see the flow slowly. The only thing that we are missing here, though, is that we are supposed to be using 130 volts. And I'm going to change this light. I'm going to double click once more on the power source, and then I'm going to change this to type 130. Of course, we are using DC, and I'm going to click OK. When I click OK, because we have a high current, you can see that the simulation now is running faster, or is showing that we had a faster current flow. Okay, and also you can notice that on each individual branch, according to how many amps is flowing through them, you either have like a faster current flow, meaning that you have more coulombs per second, or like in something like this one that have 104 ohms, that's the slowest branch, and it's because it has the lowest current. Because the more ohms that we have, the less current that we are going to have in that individual branch. So I'm going to slow down the speed once more because I want to be able to see this in such a manner that I can visualize the way in which our coulombs per second are flowing through the circuit. Our current is flowing through the different branches. Okay, so anyways, let's get started. In this instance, we are supposed to answer a few different questions from this circuit. So the very first question was that when the switch 1 and switch 2 are closed, we have to indicate the current in each meter. And as we can see here, each one of these meters are labeled beginning here, A1, A2, 3, 4, and 5. So all we have to do, because I am using FileStat, instead of doing any calculations at all I have to do is just to go back, because I know that in order to determine that current, I would be using Ohm's law. Okay, I would be saying that I would be saying that I is equal to E divided by R. A fact that we know is that each individual branch has 130 volts. That's one of the rules for parallel circuits, that voltage stay the same in each individual branch of a parallel circuit. Okay, so it would be a matter of saying 130 divided by R, 25, 52, 104, and 50, each one individually. But because, as I said, we are using FileStat, we can jump or have a head start and just get the values from the actual meters, okay? So we can see that we have 1.55 amps for A1, and so on and so forth, A2, A3, A4, and the very last one, which is A5, only has 2.6 amps, okay? Now, let's get moving. So if we start getting into the different questions we are being asked, okay, so just to make this clear, every time that we answer any of this, it's going to be from the last known position or from the last known information or piece of information that we have. So in the very first instance, when we enter all these values, okay, so I'm going to be filling this table here. And that's what I'm going to be doing. I'm going to fill the table here while we are going to be switching back and forth and do this instead of doing calculation, just using FileStat in doing all these different all these different simulations. So on the very first one, we have like 11.55 for the total current, and that makes sense. Any questions so far? Any questions?
No.
Can we use this program on our exams or anything?
I mean, like, you shouldn't because you are trying to test. Okay, so let me tell you this. I'm not there to see what you are doing when you are doing your test. It's completely based on honor, it's based on honesty. So I'm not going to be there to see what you are doing when you are doing your test. I don't even know if you open your book, if you review your handouts. That's completely up to you. However, like if you do all that, when you go to level two, that you are going to find it extremely difficult because you got used to solving circuits using this tool, right? So the reason why I'm giving you this tool is to make it easier for you to be able to find like answers and to see a simulation on how things work. But when you are in an actual test, let's say, okay, I'm gonna see you solve it. I mean, using this, you're gonna get all the right answers. But when you go to level two and then you have to sit in a classroom and do the tests without this tool that you were using in level one to do your test, then it's gonna be pretty hard. So that's my answer. Okay, you shouldn't use it, but there's nothing that I can do about it if you do.
Yeah, okay, thanks, sir.
You're welcome. So, okay, so now what we are going to do next is that we are going to open switch one. That's the instruction to open switch one to see what happens. I mean, because I have done this so many times, I could tell you off the top of my head. However, what we are going to do, let's just get into the simulation itself. And let's do that. Let's open switch one to see what happens, okay? So that one is switch one. Let's open it. And I want you please to pay close attention to what happened to this ammeter, which is A1, and to this ammeter, which is A2, okay? Why I want you to focus especially on those two? Because those are the only two meters that will be affected. Everything else is gonna remain the same. So let's take a look at that. So when we open that switch, you can see that immediately, of course, we are going to cut the flow of currents through that branch. So ammeter 2 is going to be reading 0 amps, while the total current on A1 is going to drop down. It's going to go down. Because now the only currents that are being measured by A1 are this branch, and that branch, which is over here. Okay, so we lost one branch. So when we record this, because you can see the values and we want to save a little bit of time. So what I'm going to do in this case, I'm just going to use the arrows, that up and down arrow and the check mark, just to indicate if something stays the same or if something is going up or down. So when I went back and forth, I lost the information that I have in here. So, but anyways, this went down from the 11.55 that we had before. That went down. This one then, it became 0. Okay. So the other ones, they just remain the same. So just to indicate that they remain the same, we are just going to put like this little thing that is going to look like a check mark. Any questions about that? Oh, sorry, you cannot see what I'm doing. Give me 1 second. So I said that this went down. That's what I said. And then that this one was 0. And that the other ones stays the same. Fair enough? For some reason, when I go back and forth between my what I show you on my screen, somehow this is deleted. Okay. So what I'm gonna have to do, I'm gonna have to use the actual. Actually, I don't have access to use the software like in Microsoft Word while I'm sharing my screen. So we'll just keep this in mind, like what was happening here. That was our last known position or last known information. So now let's open switch 2. So we are going to reclose switch number 1 and open switch 2 to see what happens. So let's close once again the switch 1, but now we are going to open switch 2. So when we open switch 2, of course, the flow of current to this branch is going to stop. And sometimes I ask the students, do you think that it would make any difference if we switch these two components and we put the switch on the top and the meter down here? Any ideas if it would make any difference in the way the circuit behaves?
No.
No, you don't
No.
make any difference, not at all. Thank you. I'm glad that you know that difference. I mean, that you know that you don't make any difference at all. Because at that point in time, these two components are connected in series with that resistor. So it doesn't really matter their location because they all connected in series with that item, with that resistor. It doesn't make any difference their location. So now when we did that, we can see that everything went back to normal, that from having like 6 amps before here, this current went up. This went back to normal, so it went up, of course, from 0, it went back up. And then this one went down, okay, which is A4 and A5 went to 0. So I'm going to annotate that on the screen. Okay, so I'm gonna do the annotation even when I don't have access to the previous information right here. We just gotta keep it in the back of our mind. So remember that in the past this went down, so now it went up because it went from 6 amps here to 8 amps. And this was 0 here before. So from being 0, it went up as well because it went back to its normal 5.2 amps. And all these that have been changed before, like this one didn't change at all. So that remained the same. And then this other A4 went down because it lost one of the branches that it was measuring. And this A5 went to 0.
Hey, quick question for you there. Just wondering if your audio just fell out there a bit.
Okay, sorry. Yeah, perfect. So can you hear me now?
Yeah, thanks so much. We're back.
Yeah, no, thanks to you, because I mean, like if you let me talk, I would be talking for a while and then I realized that I was muted. Okay, so anyway, thank you once more. Okay, guys, so what I was saying was that now that we have opened this other switch and we have switch 1 and switch 2 open, the only 2 branches that has power are the second and third branch. And of course, from having 8 amps, the current went down because we lost 2 branches. That's completely normal. So by all means, then we are going to say, when we go back, that this one went down, this one went to 0, and we can see that right there. Okay. We are going to say that this other ammeter, which is number 3, continue to remain the same. While, okay, like if this one from what it was before, that remained the same. And you could see this from 2 different points of view, okay? Like if you were going to say, well, but the way I did it was that I had both of my switches on, and I was having normally my 3.85, and then I opened both of them. And so I want to say that this went down. Like if you did that, it's only one item. It is okay. You can say that if you want. Like myself, I'm just departing from the point of view of the last known position, okay? And the last time that was already open before I opened this one here. Okay, so and the very last one, which is this one here, is still 0. So I'm gonna say that it's still 0. It didn't change. And the very last one now. So let me go back here. Okay, and then on the very last part, R2 opens. So let's see what's going to happen to the circuit if R2 opens up. What is R2? Okay, R2 is this one, the 52 ohm resistor. Okay, perfect. So how do we simulate that R2 opens up? Very easy. All I do is this, double click on it. And to simulate that it's open, what I'm going to do, I mean, when something is open, and okay, I got a quick question for you. When a resistor is open, does the resistor has a very, very high current or a very, very, a very, very high resistance or a very low resistance? Let's say, like it's a circuit, if a branch opens up because it creates a fault and the flow of current stops, what is it that we are going to have?
If the resistor is open, there'll be no current flow.
Perfect. And that's what I just did here. You see what I did? I just disconnected the circuit from its source. It's open. If it's open, if it wasn't there. And when that happens, okay, everything is back to normal. And then we open this resistor.
So would you consider that high resistance then? Because there's nothing?
Pardon me? If I consider what?
Would you consider that high resistance or like
Okay.
it's
Yeah.
not connected, right?
That would be pretty much an infinite resistance on that branch because nothing can flow through it. Kind of make sense? It's the same thing. Like if I were going to
Yeah,
add,
it's the same thing as it being really high. Okay.
perfect. Yeah. It's like if I were going to do this as well, like if I copy, I could also do it this way. Show you, I could pretty much come here and just place a switch. And if I open the switch, the branch is still there. The physical branch is still there. However, now we don't have any flow because that branch has developed a very super high resistance. So anyways, let me make sure. I'm gonna copy this right away so you can see where it's gonna be. So let's go back to Iconestoga. Okay. So where do you think is a good place to place this? Probably. I'm just gonna place it on their weekly lesson. Okay. And I'm just gonna create like a new file, a new link. Okay, so let's see what is hidden. I should be able to see it now. So here we went, maybe once more. Perfect. Now you should be able to find it within the weekly lesson. And it's called Falstad Circuits. Let me just refresh my stuff. Okay, guys, so let's keep moving. So please let me know, like, if you can see it. Like right now, myself, I'm having a hard time seeing it, even when I created it. Let me check. I'm gonna have to create like a brand new like folder. Holy moly. Just gonna add it as simulations. Simulations. That's what it's gonna be called. And under that simulation, that's where I'm gonna place the link. Like if I leave it on Iconestoga like that, you would be able from the Iconestoga page to do anything that you need to do anyways. If you want to open this as an external source, you can do it as well by copying the link. But I'm just gonna leave it there, on Iconestoga. So now you should be able to see it under simulations. I'm gonna put it on the weekly lesson anyways. But you are gonna see like the very first tab is called simulations, and that's where you are gonna be able to see your circuit. Okay, as soon as you click on it, you'll see it. Anyway, so now let's move into combination circuits. So the way in which we are going to be moving into combination circuits, I want to go back to this. I want to go back to this Falstad theme. And there you can see the, okay, so I'm just going to make it a little bit bigger. Perfect. So what I'm going to do in this case is that I'm going to build a very simple series circuit, okay? I'm just going to delete everything that we have. Okay. Put this back together here. Gonna delete those two paths. The reason why I'm leaving these 2 ammeters is because I want you to see that indeed the current in a series circuit is the same everywhere. And I want you to be able to see what's going to happen once we start adding different components. So let's duplicate this other resistor here. And let's connect it here in series. And we're just going to keep it like this, okay? 50 ohms, both of them. The only thing that I want to change here is my power supply to 100 volts. That way you can see that in both cases we have 1 amp, right? This ammeter here and this ammeter here chose 1 amp because we only have 2 resistors. So 50 plus 50, okay, which is the rule for series circuit. In a series circuit, which is a closed loop, the resistance around that closed loop is going to add up. So 50 plus 50, it is equal to 100 ohms. And because I show you that we had 100 volts DC, 100 volts DC divided by 100 ohms, it's going to be equal to 1 amp. So it's good. So 1 amp is coming out from the power source and 1 amp is going back. So the current stays the same on each individual component. Now, let me do one more thing here before we move on. I'm just going to go here to draw and go to outputs and add a voltmeter. When you click to add the voltmeter, okay, you are just getting 1 little point, and then you got to make sure that you click and drag the mouse so you can actually add the voltmeter. I'm going to draw the wires once more. That's a connection point. You see how it becomes like a little white point there. The node becomes like a little white point. And you may, like, if you want to feel happier because you don't want to see that minus, I'm going to press K. I press K. So I can change this minus 50 volts to a positive voltage. So we can have the right polarity. So once more, I just hover over the voltmeter, click on it, and click swap terminals. And now I have 50 volts. I'm going to do the same to this one, and I'm going to swap the terminals. And indeed, we can see that by all means, Ohm's law is not being compromised. So any questions about this series circuit? No questions so far? Now we are going to make this series circuit, we are going to convert it into a combination circuit. To do that, what I'm going to do is that I'm going to say the same thing here, duplicate. And now I'm going to be adding this other 50 ohm resistor in parallel with that 50 ohm resistor. You remember from last week when we used the formula in order to solve for resistors that are connected in parallel. If we have like 50 ohms here and 50 ohms here, those are resistors of equal value. So we can say that the RT for that little part of the circuit, okay, is going to be equal to R divided by N, meaning the number of resistors. So 50 divided by 2, because we have 2 connected in parallel, that's going to be equal to 25 ohms. So that being said, if we have 25 ohms, now, if this is equivalent to 25 ohms, and that 25 ohms is connected in series with 50 ohms, we have in total 75 ohms for the circuit. I'm just giving you the heads up. So once I connect it, then you can see it. And if you still don't get it, then I'll explain it again. So we are going to have, once this is connected, we are going to have 100 volts divided by 75 ohms, which is going to be the total resistance that we have in the circuit. Okay, so how much is that?
$1.3.
It's going to be 1.3. Perfect. Thank you. So it would be like 1 point, and okay, I'm going to use like 2 decimal values because that way it's going to be more accurate. Whichever other calculations I have to do is going to become more accurate. So let's see if these guys here are going to change to 1.3, okay? And remember, like that these two, this is measuring everything which is going through that wire, and this is measuring the return. So let's make the connection. Indeed, guys, you were right. It's 1.33 amps. And because this is now 25, right? Between this and this is 25 ohms because they are connected in parallel. All I have to do is to say 1.33, okay, 1.33 times 25. So if I multiply this times 25 ohms, then that's going to be equal to, we already have it here, to 3.33 volts. Okay, so once we do that, remember that here, and you may wonder, okay, but why are you seeing 25 when I see a 50? Remember that I told you that the equivalent resistance of that resistor plus this one, because they all connected in parallel, we were using this formula, and that gave us an equivalent, which is equal to 25. Okay, now that we have this 25 equivalent, that's why we are using this 25, because that was the equivalent resistance for this little branch here, for these 2 branches. And now that we have that information, we can see then that we have an equivalent 25 ohms. So if I want, I can do this and encapsulate those 2 resistors and call them that is a 25 ohm block. And that 25 ohm block is connected in series with 50 ohms. That's why we have 75 ohms. So just with something small like this, we have been able to use the rules for series circuits and the rule for parallel circuits. Because we were able to find that on a 25 ohm resistor that is connected in series with a 50 ohm resistor, because we were able to find that we are going to have 33.33 volts, that means that everything inside that parallel block, every component inside the parallel block is going to have the same voltage, which is one of the rules for parallel circuits. Do you have any questions for me at this point in time, guys?
Nope, all good.
So good? Does it make sense to you? It's making sense so
Yep.
far? One last thing that I want to show you in here is that what I'm going to do now is that I'm going to take this ammeter and I'm going to duplicate these ammeters. Okay, duplicate the ammeters because I want to be able to measure how many amps we have there. So I'm going to pretty much delete that. Uh-oh. Okay. I'm going to duplicate it again. And I'm going to place one there. I'm going to play my next one there. Okay, so you can see that both of them have, of course, the same current. Both of them have the same current because they are connected in parallel. Okay, so they have the same current, not because they are connected in parallel, but because they have the same value. If I were to change this value then to something like a little bit different, so let's say that I want to change this value, just thinking, so we can have like a nice number. I'm gonna use a random number. 100 ohms. Okay, so look at what happened right now. As soon as I change it to 100 ohms, like this one, now the equivalent value of this branch, of these branches, is going to be different, of course. The voltage, of course, is going to be the same. So let me show you that here, because it's they are connected in parallel. Can you see this voltage? This voltage, it has to be the same because that's one of the rules for parallel circuits. If we have this little parallel component here, inside that little block, as I mentioned before, the voltage has to be the same. But now, what has changed inside this block, because I decided to change this value here to 100 ohms, is that now we have to use the product over the sum. Remember that formula where we say 100 times 50 divided by 100 plus 50. And that's going to give us 33.33 ohms. So now these two resistors combined are putting out an effect on this total circuit, which is equal to 33.33 ohms. So that amount of resistance is the one that is connected in series with the 50 ohm resistor. Because of that, we are getting now what? 50 plus 33.33. That's equal to 83.33. So I'm going to write it down at the bottom here. That's my total ohms. And then if I use 100 volts, which is the voltage source that we are using, we are going to get indeed 1.2 amps. And then if you notice here, because we already know that the voltage is the same, 40 and 40 volts, all we have to do is to use Ohm's law to get this current is to say that we have like 40 volts divided by 50. And here we are using the same 40 volts because they are connected in parallel, divided by 100, which is right there. And when we do that, then we are going to be able to see our two different values, which is the 800 milliamps and the 400 milliamps. Okay, guys, so okay, somebody is asking a question. Okay, perfect. It's all good, someone said. Thank you so much. What I'm going to do now, I'm just going to give you a time. Like I'm going to give you a 10 minutes break. When we come back, the rest of this class is going to be a matter of practicing this combination circuit. I just showed you the beginning, okay? And now that I show you the beginning, what I'm going to do is that once we come back from the break, we're going to be getting into, okay, so once you come back from the break, this is what we are doing. Okay, so let me just get back here. We're going to go back into weekly lesson. Now, I got to tell you something which is important. Like if I go back right now into simulations, everything that I was doing there is lost. Okay, so if I go back and click, because it's a link, it's going to take me to the default circuit. If you don't want that to happen to you, and you want to keep the circuits that you draw, let's say, like if I wanted to delete all this, let's say I wanted to delete that component here, and I want to have a new circuit like this, right? All I have to do is just to click on File here. When you click on File, you will say Save as a choice, okay? But I never save it. Usually what I do, I mean, you can export it as a local file, but because I have to share this with you all the time, I never do like a local file. What I do myself is that I export this as a link. So when I export it as a link, it's gonna give me like a very long URL. So I just click here to create a short URL. And then I double click on it to highlight it. And if I wanted to, I can open like a Word page. When I open Word, I'm going to create a blank document, and I'm just going to click Control V in my computer. And then I'm going to say that this is whatever, like 3 resistors parallel. Okay, and then you know how to use Word. If you want to get back to this, you just click Control click, then you are going to be able to Control click, and that's going to open the web page, you know, like in a new different page. And now I was able to go all the way from Conestoga, where I was before. I was able to go from here, from Conestoga, and I was able to open the same thing using a complete new web page, as you can see. Okay, so it's going to be completely up to you how you want to save it. But myself, if I am doing this, I would be saving everything on the same page, because that way I don't have to be jumping through so many different files. And once we come back from the break, what we are going to start doing is that under week 4, we are going to get into some practice questions. Okay, I got to get back. We are going to get into some practice question, but the portion of the practice question, I went too far, too quickly away from that, sorry. Let me go back to the practice questions under week 4. Okay, so here, not the key, I don't want the key. I just want the practice questions. Here. Let me make sure that I can see this here. Gonna make my life easier too. Okay, so practice questions here. Even when we have a lot of crazy looking circuits, I'm just gonna take you to this portion of the practice questions, okay? In the ones where we have very, very simple circuits, which are very similar to the one that we just did. So that's gonna be the one that we are doing after, which is page 3, page 4, and one circuit in page number 5. So anyways, so let's go for a 10-minute break. And see you soon.
So you can follow along. Just give me 1 second here because I want to be able, like right now, you can see the handout that I want you to do. And what I'm going to do is that together as a class, we are going to solve the very first circuit here, but you don't have this yet. I'm going to make sure that you have access to this. So I just added this new handout, which is the one that I have on the screen. It's called, okay, so I'm going to show you this as well. So when you go to Conestoga, you're going to find this handout under the name, okay, combination circuits, practice questions 1. Just give me 1 second. It's called 1A. 1A. And right here. So it's this one here, 1A. And there you have all the circuits. So let's begin with the very, very first one, okay? Which is a circuit in which we have 100 volts power supply. We got 100 volts power source. Okay, so and then we got our 250 100 volts power source. And then we have a 250 ohm resistor here, which is R1. And you can see that the 250 ohm R1 resistor is connected in series with R2. So, okay, so let's explore the flow of current. In this instance, we can see, like, if we are going to assume, as I said before, it doesn't really matter if we use the electron flow or the conventional flow. It doesn't really matter for all purpose. On this drawing, I'm just going to assume the electron flow theory has the negative terminal right there. Our current is going to flow in this direction. It's going to be our current flowing, and then it's going to come to this little point here. When it comes to that point, which is a node, then right at this node is going to split into two different paths. Some of the current is going to flow in this direction, while the other part of the current is going to flow in this direction. Okay. The one which is flowing, like if this is the one which is flowing in this direction, we can see that first it's going to be touching R1. Right after touching R1, then it's going to go straight into R2. Also notice that without R1, it would be impossible to get to R2. That means that these two components are connected in series. That's how we can tell that two components are in series, because before this current was able to reach the folder portion of the circuit, first it has to come, bless you, on this one. Okay, first it has to come on R1. So 250 plus 750, that little branch on the top is equal to 1 kilo ohm, or 1,000 ohms. So that is that branch on the top. You have 1,000 ohms. And then our current will continue to this point here, to this node here, and this other current at the bottom, it will go through here, and it doesn't have to go through any other components, and it will also come to that point, so the whole thing can flow back to source. So by all means, we can see that we only have two branches, one at the top, one at the bottom. The top branch is worth 1,000 ohms, and the bottom branch is worth the same value, 1,000 ohms, 1 kilo ohm. If we apply the formula of resistors of equal values, and we say that, then we are going to say that RT is equal to R divided by N. That being said, it's going to be 500 divided by 2. So our total R is going to be 500 ohms. Total R is going to be, and it's very important that we always try to find RT, because once we find RT, because here we have also the total voltage, and in most cases, you will have your total voltage. Now we have 100 volts divided by 500 ohms. So 100 divided by 500 is equal to 0.2 amps. Or if you want, you can write this down as 200 milliamps. But if you do that, make sure you write that MA, milliamps.
Parker, can you grab me your sharpener, please? I do, buddy, please. Thank you.
Hot mic.
That happens sometimes. It's okay. So yeah, just make sure you'll mute it. I'm gonna delete that part from the recording if I find it. Okay, so let's get moving. So we have then, we can see here, we have 200 milliamps, and that's going to be the total. So now we had a value for this little arrow that I was pointing here. Actually, we know that this is 200 milliamps, right? We know that this arrow is 200. So 200 milliamps get into this node. And when it gets into this point, into this node, it is split into the two different branches. But we already found that both branches are the same value, right? Because both branches have the same value, of course, we are going to have on R3 100 milliamps. I'm going to write it as 0.1 just to have the flexibility. And you may wonder, okay, like here you'd write it down as 200 milliamps. Here you write it down as amps. It's just because in class, I want you to be able to see the difference, okay? The difference on how you are supposed to write it down if you write it with either milliamps or amps. Plus, for calculation purpose, it's going to be much easier to use the amps than the milliamps. For presentation purpose, it's easier just to go with the milliamps because it is easier to say I have whatever 200 milliamps than to say like I have like 0.1 or 0.2 amps. But you can say whatever. Okay, so in this case, R3, we have our 0.2 amps, okay, which is getting into that point. Because both branches are equal, current is going to split equally. So both branches are going to be getting 0.1 amp. And because now we are going to apply the rule for series circuits, the current on that component, the 250 ohm resistor and the 750 ohm resistor, is going to be the same because in series circuits, current stays the same. So now we have, just to end with this, we got to find our voltage. Okay, so this one is the easiest one to find this voltage here because you can see, I'm going to clear all this. So just to make it easier to see, I'm going to clear all this in here because now we are going to deal with voltage. And I want you to be able to see that by all means. Okay, so let's look, like if I take this little pen and I go straight down to see what that pen is touching, you can see that that pen is touching straight into R3. And on the other side, without passing through any other components, is going straight to the power source. So you can see that, yes, indeed, R3 is getting 100 volts of potential difference. So here I had 100 volts. And if you want to find how much voltage then you have between these 2 points, of course, because they are equal, okay, let me take that back. When I say they are equal, like this little section here, which is 1,000 ohms, it is equal to this branch, which is at the bottom. Plus, if we use the same pen, I'm going to delete this. If we use the same pen, the same marker, we can see that now it goes to that portion of this little block, which is worth 1,000 ohms. And then it goes to, it keeps going from here, and it goes straight back into the power source. So that little block has 100 volts apply. But I mean, but that little block, internally, it's a split into 2 different components, which is R1 and R2. So what we do, we know that, yes, the block had 100 volts. So that means that we are going to have to apply the rule for series circuit and say that the sum of the voltages in a series circuit is equal to their source voltage. But because we already have the value for current, we know that 250 times 0.1, okay, the 250 ohms, time we have here 250 ohms, which is the value of that resistor, time 0.1 is going to be equal to 25 volts. And then the same thing here, 750 ohms times 0.1 is going to be equal to 75 volts. As you can see in here, then 25 plus 75 is equal to 100 volts, which is the amount of voltage that is being applied across this block, which is a series block. And this is the basis for a combination circuit. What I want to do next is that I want to give you time. I want to give you like 5 minutes for you to explore the next two following circuits. So I'm going to clear all these drawings so I can show you on the screen. Now I want you to, like, as I said, I already uploaded this to Iconestoga. So please make sure you go to week 4. So under course content, you are under week 4. And then you get straight into combination circuits practice 1A. That's where we click. And that's where you find all the circuits. The 6 circuits that I want you to do first. Okay, so we already solved this one together. I'll give you like 5 minutes. I'm just gonna be here, like if you have any questions. And then I want you to solve 2 and 3. And then we are gonna be solving together number 4, okay? The time is yours. I'm just gonna set up a timer for 5 minutes. And you are not gonna see this on the screen, you are just gonna see the timer, okay? So make sure you open Iconestoga, do like that young man that was looking for a pencil, and get a pencil, please, and paper, and get to work.
Good now.
Pardon me?
We're good now. I'm all sharp.
You're good? You finish it?
I got my pencil sharpened.
Oh, you got your you got your pencil sharpened. That's great. So go ahead, man. They on those 2 problems and practice with them to see if everything is getting home, you know. So I'm gonna be muted, but I'm still here. Okay, guys, so I'm just wondering if you had a chance to finish the 2 circuits, or if you need a little bit more time to figure it out. Please comment.
A little more time if possible.
A little bit more time? Sorry, I missed you there. You said you want a little bit more time, or we can keep going?
Myself, I completed one of them, but I'm still working on the second one.
Okay, so yeah, that's good. That's good. So I'll give you like a few more minutes. I'm not gonna put a timer this time. So as soon as you are done, start saying on the chat, like, just write done. And that's it, okay? Remember that if you have any questions or doubts, shoot, just let me know.
I just have a quick question on number 1 there. Wouldn't your resistance total be 2,000 ohms?
So
it's
for
up
the
to 2
first
resistors.
one, for the very first one, right?
Yeah.
Yeah, you got to keep in mind that they are connected in parallel. So we have to use, we have like 2,000 ohms in resistance, but that's not the total resistance because they are connected in parallel. If you were to connect them in series, yes, you have 2,000 ohms, but if you connect the same resistors in parallel, then you have 500 RT.
Okay.
Thanks for the question. So it seems that a lot of you are done so far. Anybody else need a little bit more time, or we can keep going?
Just got a quick question. For our test this upcoming Friday, is it going to have series, parallel, and combination circuits on it?
Yeah, it's gonna be simple combination circuits, but still it's gonna have combination circuits.
All right, thank you.
You're welcome. So now let's get moving. On the next circuit, in the next circuit, that you can see it right there, which is number 4. Like in the case of number 4, so let's do the same thing that we did before, okay? In this instance, we have one resistor. So let's use a current. I'm gonna mimic that this is my current flow. Current is flowing this way. So when current flows, this is the total current. The whole thing is going to flow through R1 first. And when it goes through R1, then it's gonna come to this joint here, and it's going to split into 2 different paths. Some of the current is gonna go this way, and some current is gonna come this way then. Okay. So somebody asked me just to review the other 2 before moving forward. So I'm just wondering if you have any questions about any of those.
Yeah, I'm still unclear as to how you're calculating your resistance.
Oh, okay. So yeah, sure, fair enough. You know, now that I have a specific question, I can show you. In the case of
Can we go over the whole thing just to be safe? Make sure we're on the right path before we go through the whole thing, seeing it's going to be on the test on Friday.
Okay, so like here, you can see that we have what? We have the power source. So if we use this current, and the current starts to flow like from the negative terminal, then it's gonna come to this joint in here. And when it comes to this joint, then it's gonna split into 2 different paths. So some of the current is gonna come this way. So we can rejoin at this point, at this node. And some of the current is gonna come this way. The reason why I wasn't planning to explain this one to you is because I explained already number 1, and this is just the same process with different values. So if you look at this guy, it's gonna be the same thing that we were doing before. This R2 and R3 are connected in series. Because they all connected in series, we are just gonna get a block from those 2. And this little block that we get from these 2, because they are in series, is gonna be equal to 1.75 ohms or kilo ohms, sorry. So we have for this little block 1,750 ohms. And that little block is connected in parallel with this one, which is R1, which is a 250 ohm resistor. So when now we use the formula, which is the product over the sum, because they are resistors of different values, we say, okay, so I have that RT is gonna be equal to that value, which is 1,750 times 250, then divided by the sum of these 2. So what's gonna be the result of this little equation?
218.75.
It's gonna be 218?
Yeah.
0.75. Thank you. So that would be all RT. And that's the value that we are getting here, 218.75. Now, we already know the value. I'm not going to be writing just because of convenience. I'm not going to be writing down the values for these ones because we already have them here. The 250, 750, and 1 kilo. Okay, so what was the next step to do? As we said before, you can see that this line is touching without passing through anything else that side of the resistor of R1, and the other side is going back to source and is touching the power source, the battery. Okay, it's touching that pole without going through anything else. So by all means, R1 is getting 100 volts. So the voltage on R1 is 100. Now that we know that we had 100 volts and 250 ohms, we can determine how many amps we have in there. So we have 100 divided by 250, that's going to be equal to 0.4 amps. Okay. Now, you may tell me like, okay, but we haven't found out how much current. Okay, I put this on the wrong spot, 0.4 amps. So here. So we have to find out how many amps we have total. Okay. We already have RT, which is 218.75. So 100 divided by RT. That's equal to 0.457 571. Okay. Now, this is a very important step. I want you to notice that we are going to have a total current, which is the 0.571 amps. The whole thing is flowing through this conductor, and it comes to this point in here. Okay, that's a very important step. It comes to this node. Because we already use Ohm's law, we already know how many amps go through this R1 branch. So we already know how much go this way. So of course, because energy cannot be created, whatever is left, then whatever is left has to be going through here, through this one here. Okay, so we already know that we got 0.4 going through here. So how much do we have left?
0.57.
Perfect. So we got 0.057. Now here then, with all confidence, you can see that the 0.057 amps, which is 57 milliamps, first is going to go through R2, and then once it finishes with R2, before it gets to R3, you got to go through R2, but it's going to be the same 0.0057 amps, because we again apply the rule that says that in a series circuit, current is the same. And this is a series branch. So that would be 0.057. And this one would be 0.057 as well. And because we know their own values, 750 and 1 kilo, all we have to do is to use Ohm's law in order to determine the applied voltage. By all means, that voltage plus that voltage here has to be equal to the source voltage, because I told you before, I told you that within this block where we have the 750, okay, full voltage is being applied to that little block that has two resistors connected in series. But let's see how much is going to be the voltage of each independent component. So we use Ohm's law and we say, okay, 750 times 0.0057. So one of them is going to have 42.75 ohms. And if I take the other 0.057 times 1,000, of course, that's going to be equal to 57 volts. And you can see that 42.75 volts, we could round it up to 43 plus 57 volts is going to be equal to 100 volts total, which is the applied voltage on this little block. The reason why we have this small discrepancy of 250 milliamps, it is because we were not using all the decimals. Had we been using all the decimals, then we would be getting here the pretty much a 99% accuracy of the total value. Are we okay there? Any questions about this problem, or can we move on?
I think we can move on.
Okay, so let's get moving then. I'm gonna clear this one. So on this problem, same idea. I guess you're already used to the idea that, well, that these two are connected in series. So let's draw the little block once more here. And now that inside that little block, or this little block, is worth 1,000 plus 250. So that would be 1,250 ohms, because they are connected in series. How do we know once more that they are connected in series? Because for my current, when my current comes this way, in order to make it to R3, it has to go, like in this case, through that resistor, which is R1 first. Okay, that's how we know that they are connected in series. Because one component cannot get any energy unless the other component get it first. They are not independently connected to the power source. They depend on each other. Now, we are going to use the same product over the sum. So then we are going to say that we have 250. Okay, so 1,250 times 750. Divided by the sum of those two. What is the total value for that, please?
468.75.
Okay, perfect. So that's going to be the value here.
Attaboy.
468, thank you. 0.75. So that's going to be RT. And then let's do the same process. As you can see, this becomes repetitive in a sense. And the same process will be, well, now that I have RT, I'm going to take my 100 volts divided by the 468.75 to get my current. In this case, we have 0.2133. Okay, that's got to be my current. Now that I have my current, the total current, of course, we know we had 100 volts. Okay, so again, the same thing that we did before, right? Which is we can see that by all means, that this wire is connected straight to that R2 resistor. And this other wire here is connected straight to the power source as well. That means that R2 is getting full voltage. In this instance, 100 volts here. And because we already know the value for R2 to be 750 ohms, using Ohm's law, we can determine how much current we have, which is 0.133. Okay. Now that we know this current, we can see that my total current is going to come through this wire. It's going to come to this point. And I'm just repeating the same thing that I repeated before. And then this amount, which is the 0.133 or 133 milliamps, will come this way. So whatever is left, okay, so it's coming this way. And that would be 0.1, right? According to my calculations here, how much are you getting? 0.0803? So I'm getting here. Okay, so whatever is going through R1 and R2 is going to be 0.0803. That's what I'm getting for both of them. But the question would be, do we know why R1 and R3 has the same current?
Because they're in series?
Because they are in series, and the rule says that in series circuit, current is the same at any given point. Now that we have these currents, we can use their resistor values, our 250 ohms and our 1 kilo ohm, in order to determine their voltage drops. So this one is going to be equal to 20 volts. I'm going to write it down like that. It's 20.1. I'm going to round it up. And this one is going to be equal to 8.80. Because of their, we are not using all the decimals. We have a small slight discrepancy, but it adds up to 100 volts. So you could have a discrepancy of a few millivolts, but you shouldn't have a discrepancy of, let's say, like 5 or 10 volts.
Could you give a break? Could you give a
Pardon me?
breakdown of how you're getting 468.75 for total resistance from that calculation? Because I can't get that number from that calculation.
Oh, okay. No, I was given this number. Somebody told me this number, and somebody
Yeah,
else said, "Attaboy."
I just don't understand how that 1,250 times 750 divided by that number gets that number, 468.
Let me check.
Like, are you finding the reciprocal
I
of?
also am wondering.
Go ahead, Perry.
No, I don't understand why why are we confusing everybody with this formula? Why can't we just use the reciprocal formula for
Yeah.
all these situations to make it easier for everybody? Because
Okay,
I just
'cause
feel like everyone's confused over this formula.
that is absolutely
Just
where
'cause
I'm
you
lost.
It's just because you still need this for when it's just two resistors. So you're simplifying this branch into two resistors. So one is adding 250 plus 1,000, and then the other one. So you have two resistors. It's a simpler equation than the reciprocal.
The
But
reciprocal
is
is
it
the
really?
way we
Because
were
you're just
taught, though.
dividing numbers.
It's multiplied by multiplied divided by addition. So it's like it's less than 1 over 1 over 1 over 1 over.
Yeah, that's why I was using that, because it's a more condensed formula. It's simpler to use.
But we all have calculators. It's just 1 divided by, and then 1 divided by, and then like use your brackets in your calculator. It's faster. But I just feel like everyone's getting stuck on this formula.
I'm
It
big
is
time
completely up to
confused
you.
on
Okay,
this.
so let me show you. So all you are doing is, like, when you did your 1,250 times the 750, that gave you 937,000. 937,500. So you take that value and you divide it by 2,000. Because 1,250 plus 750 is equal to 2,000. So you divide that amount by 2,000, and that's it. That's how we are getting, like, that divided by that is getting 468.75. And it's just that I am used to the fact that whenever I only have two resistors, I myself never use the reciprocal formula because it's more steps. As soon as I see two resistors, I just do product over sum because it's quicker even in the calculator. But if you feel that you are going to be better served by using the reciprocal, by all means, go ahead and use the reciprocal. It's still going to be the same thing. Make sense now that you see it broken down like this?
Yeah, it definitely helps. It just felt like there was maybe a step. Maybe you went a step ahead before I could understand where you were getting this, but I understand it now. It makes sense.
Okay, perfect. So what about all these numbers
that makes sense?
That makes sense as well?
Yeah, because once you have the resistance total, then you can calculate for that, right?
Yeah. So let's move to the next problem here. The next problem that I was going to show you before we got into that is this one here. And what we have here, now you can see that we are going to have a current that is going to be departing from the negative terminal. This current first is going to go through R1. The whole current is going to go through R1. And then it's going to come to this node, to this point here. And when it gets to that point, then it's going to split into two different paths. It's going to come this way, and it's going to go that way. Okay? That means that the current then is going to go through R2, whatever R2 is taking and whatever R3 is taking. And then that current is going to recombine on this other node here. And the whole thing is going to flow back. It's going to flow back to source. The reason why I'm showing you how the current is flowing is for you to see how the circuit is connected. You can see now that R2 and R3 are connected in parallel, and we are going to use parallel circuit rules to solve for them. And at the same time, this parallel block is connected in series with the 250 ohm resistor. So now let's get to work. Let's solve for the parallel block first. Why do we always solve for the bigger component? Because we have to simplify our circuit. So we can see that this little block is a parallel block. I use two components that are connected in parallel. Again, if you want, you can use product over the sum. That's what I'm going to use. But you can use the reciprocal formula as well, okay? So if I were going to use the reciprocal formula, we got 750 and 1,000. Well, let me do this, okay? I'm going to use both. I'm going to use the reciprocal with the first one, and then I'm going to explain number 5. And for number 5, I'm going to use the other formula, which is the product over sum, okay? So if we do this, we got 750. Remember that key? Plus 1,000. Press that key again. That is equal to that amount. Let's press that key again. And then we have a total of 428.57 ohms. 428.57 ohms. So let me get back and share this with you. So on the little block here, for these two resistors, we have 428.57. So I'm just going to keep that in mind. Okay, so now this 428.57 is connected in series with 250 ohms. So we just add the 250 ohm to it. And we get a total value, a total R value of 678.57 ohms. That's the RT. We had 100 volts sourced. So what we do, we use Ohm's law once more, and we say, well, 100 ohms divided by my 678.57, that is equal to 147.36 milliamps. Okay. So, but because it's more convenient just to write the decimals for calculation purpose, I'm going to use small numbers this time to see if we can get closer to a more accurate value, okay? And that's enough. I'm using 5 figures in this case. So far so good. Any questions about that?
Nope. Nope, good.
So all good. Okay, so now let's see. Can you see, remember that I told you that the whole current that is leaving that pole, that is leaving the negative terminal, the whole of it is flowing through R1. Do you agree with that?
Yep.
So that means that we already found, like by finding IT, which is the total current, we already found how many amps we have on R1. And if we already found this current, because we already know how much is this ohms or this admit value, then we can determine how much voltage is being dropped at that point. So we'll say now 250 ohms that we have times the 0.147 or 147.36 milliamps. You get here 36.84 volts. Fair enough? So I want to call your attention to the following. Remember that this little block here is connected in series with that one, right? So from here to here, can you see that this is just an equivalent resistor, which is worth 428.57?
Yep.
That means that I can find my total voltage by using the rule for voltage in series circuits. In a series circuit, voltage add up. So now I have my 100 volts sourced minus the 36.84, and that is equal to 63.16. Inside the little block, I have to apply parallel circuits rules because they are connected in parallel. So that means that voltage is the same for both components. And now that I found my voltage for those two, I can use their resistive value, my 750 ohms with R2 and my 1 kilo ohm with R3, and I can find my current. So that means that 63.16 divided by 750, that is equal to 0.0842. And I'm going to do the same here, 63.16 divided by 1,000, it is equal to 0.0631. Now, something important, if I want to verify that these values are correct, by all means, these two values has to add up to my 147.36 milliamps. So let's add these two values here to make sure that yes, indeed, my whole calculation is correct. So when I add this value plus these values, I obtain 147.36 exactly. Why? Because as I showed you before, okay, the whole current, which is my 147.36 milliamps, gets to this, go through this resistor, then it gets to this point, here, and when it gets to this point, it splits into two different paths. Then it's going to be splitting into this path, which is R2, and it's going to be splitting into this path, which is R3. Later on, they're going to flow through their respective components. And then at this point here, they are going to join back together. And when they join back together at this node, then the whole of it is going to flow back to source. How much it was entering the node? 0.1 or 147.36 milliamps. How much it has to be leaving from there? The same amount. It cannot be more, it cannot be less. So that means that the sum of the two branches, the current, the sum of the current of the two branches, they have to add up to the total current. Any questions about that, or we are good? Okay, somebody say what? I don't understand the question.
No, sorry, I get it. No, my bad. Yeah, I'm good.
Oh,
Thanks.
okay, perfect. Don't be shy. Like, I mean, if somebody say a question like that, what? I can explain anything you want, but I have to know what. Okay, guys, so let's keep moving. So we're good?
Yep.
I mean, this takes practice, okay? This takes practice, and it's a matter, like, if you cannot see it there, please remember that you can go to FileStat, build a circuit, and see how your current flows. Put the different meters, and that way you are going to be satisfied, okay? Like, okay, now it makes sense that because my electrons are flowing in this manner, that's why, you know, that all these values cannot be altered or cannot be violated using Ohm's law. Everything has to match 100% all the time. So let's keep moving. So in problem number 5, and as I said, I'm going to use product over the sum. I already explained what we were doing here, but I will. Oh, yeah, that's true. Somebody said that in the end, you get the same answer. So whatever is easier for you. Absolutely right. It's like different ways. We can always use different ways to get to the same answer. And you will see that when we get into Kirchhoff. So anyway, so this is the plan for now. I'm going to explain this problem to you, and then I want you to do number 6. And then after that, we're going to be jumping into another problem where we are going to be using Kirchhoff in order to solve for the circuit. But it's going to be a little bit more complex than what we had on the screen right now. So we already established that, okay? We already established that this is my total current, that the total current has to flow in this case through R2. That's the one which is there. And then it's going to come to this point here, which is called a node, N-O-D-E. That point in time, then it's going to be splitting into 2 different paths. Some of the current is going to go through R3, and some of the other current is going to be going through here, through R1. They're all going to recombine right at this node here. And when they recombine at that node, then the whole thing is going to flow back to source. We already established that. So we also established before that R3, in this case, and R1 are connected in parallel. So let's go ahead and use product over sum. We're going to have 1,000 times 250 divided by 1,250. So if we go to our calculator, we have 1,000 times 250. That is equal to 250,000. So we are going to take out 250,000, as you can see in here, divided by 1,250. And that's equal to 200 ohms. So my RT like this equivalent resistor here is 200 ohms, right? I already found that within this box here, I have 200 ohms. And that little box is connected in series with 750. So 750 plus 200 is equal to 950 for our total. 950 ohms. Same process. We got 100 volts for the power source. Okay, so having 100 volts means that now we have 100 volts divided by 950. That is equal to like 0.10526. And I'm gonna use 5 decimal values just because it's gonna make it more accurate. 105.26 milliamps. Okay, so now that we know how much is the total current, okay, so we already agreed before that that total current is gonna go through the 750 ohm resistor. So I'm gonna take my 750 ohm resistor and multiply my total current.
That's actually R2.
Shouldn't that be an R2 column?
Yeah.
Oh yeah, thank you for spotting that. Thank you. Perfect. So it's gonna be on the R2 column. And R2 is gonna be like 105.26. Perfect. So we do the same thing we did before, which is that we are going to take that number and we are going to multiply. Okay, we are going to take this number and we are going to multiply by 750 so we can get the voltage drop that we have there. Okay, like in my case, I'm getting 78.94 for my voltage drop on R2. I'm almost tempted to say 80. Okay, I'm just gonna round it up to 95. Because it was 78.9473, blah, blah, blah. So let's round it up to 78.95, okay? And now with that value in mind, then we can see that whatever voltage is left is gonna be 100 minus this. So that's gonna be equal to 21.05 volts. So we are getting, because of parallel circuits rules, because inside this block, they are connected in parallel, 21.05 here, and the same value of 21.05 here. And now that we know the voltage values, then I'm going to divide my 21.05 by my 250. So on the first one here, I get 84.21 milliamps. So I'm just, I'm gonna write this down here. So like 0.0842, I'm gonna say. 842 amps here. And then same thing here, it's repetitive. Okay, the same 21 volts. 21.05 divided by 1,000. So I'm getting there 0.0210 or 21.05 milliamps. Now, when we add, and this is a very important step, when we add these two numbers, so when we add this number here, with this other number here, they have to add up to the total current. So are they adding up? Let me just verify that. In my case, like I can see that they add up perfectly. They add up to 105.25 milliamps. So I have 1 milliamp, you know, because of the decimals, but it's a pretty accurate value. So you were able to see as well that if we are using, so instead of using like 3 decimal points, like if we are using like 5 figures, you are going to get very, very accurate information. So now, guys, I'm going to give you 5 minutes. Do you have any questions about this? No? Okay, so I'll give you 5 to solve problem number 6. And now the time is yours. 5 minutes, solve problem number 6, please. Okay, guys, so any questions about this last circuit that I gave you to do? Are you done already?
Yeah.
All good, perfect. So let's get moving. So to finish in today's class, I want to show you how to solve a circuit, which is a little bit more complex than the one that we were seeing before. So So now you have a circuit which is a little bit more complex, and we are going to apply the same idea that we have been using so far. In this instance, okay, so I want to point out that you have like how many, like 1, 2, and 3 resistors that are that I could say are like inside this little box, inside the yellow box there. And then we have, okay, so if we follow the current through, okay, we got current. It's going to be coming over, and the whole of it is going to go through R1. The reason why I know that this is R1, even when it doesn't say it there, is because right on the top, it reads E1. So E1 refers to the voltage that is being applied to R1. I'm going to use a different color here to make it easier to see. Okay. So this is getting full current. How much is that full current? 5 amps. Then it's coming to this spot, to this node here. So it comes to this node, and when it goes to that node, then your current splits into 2 different paths. Some of the current goes, some of the current is going in this direction, some of the current is going in that direction. The one that goes in this direction, okay, it's gonna keep going. It's gonna go through R3, then it's gonna come to this other node here. The current which is going in this direction, it will first go to R2 before it can even make it to L4. And then once it goes out R4, then it's going to make it to that node. They are going to recombine together like this and that current. And when they are recombined together, the whole of it is going to go through R5. So just by explaining how the current flows, and just by seeing how the current flows, we can tell right away, we can deduct right away that, well, I1 is equal to 5 amps. And we can deduct right away that this one, which is I5, is also equal to 5 amps. Any questions about that? So far, so good? So that being said, thank you. So that being said, then we can use Ohm's law, and we can say, well, 100 volts divided by 5 amps, that is equal, or that is telling me that R1 is equal to 20 ohms. 100 volts divided by 5, 100 by 5, 20. Right here, we are going to use, like if we want to find R5, remember the pie chart? That's why it's so important to know all these formulas. Then we have now watts and we have current. So we can apply this formula that says that, okay, P is equal to I times E. So I already have P, and I already have also my I, so I would be able to find my E, and then I would be able to use Ohm's law, okay? However, there is another formula that says that P is equal to I squared R. And I was asking you to find R right off the hop. So let's do that. So if I want to find this R, all I have to do is transpose. And this I square, which is multiplying R, is going to go to the other side of that equals sign, performing the inverse operation. So when we rearrange the formula, we have that R is equal to P divided by I squared. So then we have all 500 ohms. Okay, so we got our 500 ohms. Okay, give me just 1 second here. Perfect. I don't want to lose everything that I have on the screen, so I'm just going to leave whatever I have there. So like if you have a calculator, would you please help me out in doing the calculation? We got like, pardon me?
20 ohms?
Yeah, perfect. It's got to be 20 ohms. Beautiful. It's sadly 20 ohms. Perfect. Thank you. So that means that, of course, if we have 20 ohms, we are going to be able to find out using Ohm's law how much is the voltage drop here and here. So here we already have like 100 volts and 5 amps. So if here we have like the same 5 amps and both of them are equal, of course, here we have 100 volts as well. But also we could have said 20 ohms times 5 amps, 100 volts. Okay, so now let's concentrate on what is inside that little box. In this box, we already established that R2, which is 40 ohms, and L4, which is 20 ohms, are connected in series. So the equivalent of these two resistors connected in series is equal to 60 ohms. Now, that 60 ohm, we can see that it's branching off like the 60 ohms with the 30 ohms. So now we have in parallel 30 ohms with 60 ohms. So 30 and 60 ohm in parallel, it is equal to 20 ohms. So if you, I'm gonna give you a little bit of time so you can do the reciprocal and you can follow through. And please try to see if I am right. If when I say 60 times 30 divided by 90, will I get 20 ohms? Or if I do the reciprocal formula with 30 and 60, will I get 20 ohms? Just confirm that information, please.
Yes.
Yes, we do. Okay, so we see that in the litter box, we have 20 ohms. And because we have 20 ohms on the litter box, on that litter box as well, we have 5 amps. Because remember, the litter box is just, it becomes just one equivalent resistor, which is connected in series with R1 and R5. So yes, indeed, we have 20 ohm, 5 amps, and of course, we have 100 volts. If I were going to redraw the circuit looks like this. I have R1 here, R1 here, and then this one is an equivalent resistor, which is 2, 3, 4. And this one here is number 5. So that is 100 volts. That one is 100 volts as well.
Wouldn't there be voltage drop between one and the letterbox?
Yeah, the 100 volts is the voltage drop.
Okay.
Because I didn't give you how much is your total T or your ET, your total voltage. Okay. So in this case, you found, and that's what I'm getting into, that because we had 100 volts drop on this one, the equivalent 2, 3, 4, and 5, that our ET, the total voltage applied, is equal to 300 volts actually. That's going to be this value here. Okay. Now, this is the most important step. Look at what I'm doing here, please. As I said before, I already told you that we have, yes, 20 ohms, which is the everything which is inside the yellow box. And then I have, from this point, I have an equivalent resistor, which is worth 60 ohms, which is the 40 and 20. And then the other one is 30 ohm, which is by itself. Now, because these two values are in parallel, okay, they are receiving the same voltage. So this value, which is called E3, is equal to 100 volts. Why? I want you to notice once more, if I were to use a voltmeter and connect it between this and that point there, the voltage drop between these 2 points is equal to 100 volts, which is that point and that point in there. Now, because that resistor, which is all 3, is connected directly to those 2 points, is getting full voltage, 100 volts, which is the voltage for that portion of the circuit. However, By the same token, you can see, and you can say, well, so does that mean that the 60 ohm equivalent is also getting 100 volts? Yes, indeed. That will mean that E2 plus E4 will be equal to 100 volts. And we'll find that in just a minute. Now that I have two values for E3, which is for R3, sorry, which is my resistor value and also my voltage value, I can find I3, which is my current. So I3 is equal to 100 divided by 30. How much is that, guys, please?
3.33.
Perfect. Thank you so much. 3.33 amps. Okay, so I have 3.33 amps. This vector here is worth 3.33, which is whatever is going through that resistor. Do you remember how many amps was getting into this point here? How much was coming in?
5 amps.
5. So if 3.33 is going this way, whatever is left then is going that way, which is 1.67 amps. 1.67 amps is going that way. So if 1.67 amps is coming this way, 3.33 plus 1.67 is equal to 5 amps. So if 1.67 amps is coming this way, then now we can find the voltage drop through R2 and R4. Because this current, it will first come through R2, and when it does its work on R2, it will carry on to R4, but it's going to be the same current because that's a series component. And just to finish with this, we have that 40 times 1.67 is equal to 66.8 volts. And then the same value, 1.67 amps times 20 is equal to 33.4 volts. And by all means, once more, the series circuit rule applies. That voltage of R2 plus this voltage of R4 is going to be equal to the voltage that we are going to encounter between these 2 points, which is 100 volts. Any questions about that? So after that, it's going to be a matter of just filling in the blanks because we already found all the different values for this circuit. So I want you please today to take the time to go through the other circuits. Like if you look at something like this, keep in mind that these two resistors are connected in parallel, and be mindful of the fact that you are only being asked these 4 questions. Okay, so keep in mind these two resistors are connected in parallel. These two here are connected in series. And then whatever you have in series here is connected in parallel to that one here. Okay, so you just got to look at the circuit, and because of the way the current flows, determine how is it that they are connected. If I were going to do this with current, okay, so I'm going to say that, well, my current is going to come to this node So as soon as I see a node, I know that there's a parallel component. So when I see a node, I'm seeing a branching off. Something is branching off. As soon as I see a branch off, I have parallel branches. So some of the current is going this way, back to this node, and some of the current is coming this way. So you can see here that because for this one to be able to get its current, it first has to flow through R5, and they depend on each other, that this is a series component. So once more, I'm telling you, here you are not being asked to find RT. Okay, I didn't even give you like a total voltage, as you can see in here. So you just have a schematic with a few different values. So just limit yourself in this case just to find these 4 values and nothing else. You don't need to find anything else. Okay, so again, when the current joins here, it's going to continue straight and then split up again into 2 different paths. So that means that these 2 branches are also parallel. So, and the reason why I'm saying this is because every time that you see the something series circuit rule apply. And every time you see parallel branches, then parallel circuit rule applies. So you got to keep that on top of your head, because that's all you are doing at the end of the day is solving everything which is parallel, solving everything which is series, so you can simplify the circuit to just one single resistor. Any questions? Let me advance a little bit more. Like if you see something like this, again, please pay attention to the information you are being given on the top. Okay. And here, the only value that I'm asking you to find is RT and nothing else. You don't have enough information to find anything other than RT. How you are going to find RT in this instance? Using Ohm's law. You have your total voltage, you have your total current. Okay, so actually this one says that you have 3 milliamp through R1, so make sure you read the information, and it's going to be very, very simple to find RT. Now, when you have something like this, where you have to find a bunch of information, still it's going to be the same idea. Okay, so if I am going to suppose that current flows this way, the whole of it is going to flow through R1, and then it's going to come to this point where it's going to split up into 1, 2, and 3 different branches. So if I explore what is in the first branch, I can see that my current is going to go undisturbed to this node here, right? And also I'm going to see that this other current is going to go undisturbed to that node here as well. So that means, okay, those are my 2 points, that R2 and R3 are connected in parallel. They are connected to the same common points. Now, as we continue to see, once this current joins here, then these 2 currents will flow to come through here. So just to simplify your life, and this is the last thing that I'm showing you today, if I were going to find RT, and let's find RT together, okay? So the way I'm going to start solving this circuit or simplifying this circuit is the following way. I'm going to say, okay, listen, I know that R2 and R3 are connected in parallel. So let me start to redraw the circuit. And I'm going to say that, okay, this is R1, which I already know is 12 ohms. And then I'm going to have my leader point. I'm going to draw my leader point here. Okay. And I can see that right from this point, I have two resistors that are connected in parallel, 12 and 6, which is R2 and R3. So I'm going to redraw that as just one single resistor that I'm going to call 2, 3. And that I'm going to give a value of the resultant, which is 4 ohms. Is it 4 ohms? Can you check, please?
Yeah.
Perfect. So remember this other point here? I'm going to redraw that point as well here. And to that point, then, what is connected to that point? I can see that now I have my 5 ohm resistor connected to that point. That's indeed 5. This was 1, and this is 12. And this is R5, which is 20 ohms. Okay, and then let's be careful here. Okay, guys, so you can see here that this goes back, and then there is another point here. So I'm going to draw this little point here. And you can see that in between these 2 points, we have another resistor that I didn't touch yet because I'm trying to simplify this step by step. And this is number 4, which is 24 ohms. Okay, so now all we got left is just to draw the wire back to the source. So you can see how we simplify the circuit slightly. Now, look at this. Right at this point in time, you can see that this 4 ohm, which is 2 and 3, just by looking at it, like if my current is flowing through here, it's going to go through 2, 3, and it's going to go straight to number 5. So that means that 2 and 3 is connected in series with number 5, which is 20 ohms. So we apply series circuits rules. So we have a new equivalent resistor or a new equivalent circuit. And I'm going to ask your permission to do this. So like in this case, what's going to happen, as I was telling you, is that now we can see that the 2, 3, the resistor, the equivalent one, which is called 2, 3, which is equal to 4 ohms, it is connected in series with the 20 ohm resistor. I'm just going to modify the circuit slightly. I'm going to erase this part here. And I'm going to add that 20 ohms to these 4 ohms, so I get 24 ohms. But now this equivalent resistor is going to get a new name because now it's also accounting for the 20 ohm resistor. So now equivalent resistor 235 is equal to 24 ohms. So they are joined here. Okay, so now I want you to observe this as well, guys. You can see that here we have a connecting point, which is a node, and here we have another one. And now my 24 ohm resistor is connected between this and that point directly. By the same token, this other resistor, which is R4, is also connected to the very same points. That means that these 2 resistors are connected in parallel. So I have that 24 ohms in parallel with 24 ohms. That's going to be equal to 12 ohms. So I'm going to erase this here, because now I have a new equivalent resistor that I'm going to call. I'm going to write it down first before I delete it. This new equivalent resistor is going to be called R2, 3, 4, 5. And it has a value of 12 ohms. These 12 ohms came from the fact that 24 and 24 connected in parallel is equal to 12 ohms. Now I can delete all this. And when I delete all that, okay, this is the remaining resistor that I have. You can see that my remaining resistor which is 12 ohms, is connected in series with R1. So I'm going to apply series circuit rules. So 12 plus 12, that's going to be my RT, is going to be equal to 24 ohms. Now that I know that I have 24 ohms for my RT, and I have 24 volts for my total voltage, well, 24 divided by 24 is going to be equal to 1 amp. So I'm going to show you how to work everything backwards, how to apply Kirchhoff in order to find all the different values that you need to find in this circuit here. In order to do that, I'm going to apply the following. Okay, so let's begin to see. I already found my RT to be 24 ohms. I already know that I have 1 amp. So that means that my current, which is flowing through here, is equal to 1 amp. So I1 is actually 1 amp because the whole of it, the whole current, is flowing through R1 before it can make it to this junction in here. Okay. Now, something else that you got to keep in mind is this. Okay. Here we have what is called a closed loop. Remember that we were talking about closed loops in series circuits? And if we have a series circuit and we have a closed loop, the voltage around this closed loop, that is Kirchhoff voltage law, is going to be equal to the source voltage. That means that, well, I found here to have 1 amp. And right here, I can find my E1, which is equal, in this case, to 1 times 12. So that's going to be 12 volts. And when I apply Kirchhoff voltage law, then I have that the algebraic sum around a closed loop will always be equal to 0, which in other words means that the sum of this voltage here around the closed loop plus this voltage here got to be equal to the source voltage. So my 24 volts, which is my source voltage, minus these 12 volts that I have for R1 is going to be equal to E4, which in this case happen to be 12 volts as well, because it's going to be 24 minus 12 equal to 12. So we can see that the rule, this law that around a closed loop, the algebraic sum is going to be equal to source voltage applies. We can use that, okay? You still haven't seen an evidence of that, but once you have all the calculations in place, then you are going to be able to see that everything matches, that there's evidence to that fact. So right here, I'm going to complete this and I'm going to say that I have 12 volts. Next, now that I know that I have 12 volts here, I can determine my current. So my 12 volts divided by my 24, I got my 12 volts divided by 24 ohms, that is equal to 500 milliamps, or I4 is equal to 0.5 amps. Okay, so now that I know that I have 0.5 amps that goes this way, remember that we only have 1 amp coming this way. If 0.5 comes this way, then how much is going through these other two? I want to bring your attention back to the fact that I told you that these two resistors are connected in parallel. And then when the current joins, whatever it is going to flow through here. So through this resistor, we also have 0.5 amps, same current. Why? Well, because if I have 0.5 amps coming down, then I don't know how much is going that way. I don't know how much is going that way at this point in time, but I know that the sum of that plus that has to be 0.5. It cannot be less, it cannot be more. So that means that when it comes out and they join at this point, 0.5 is going to be joining at this point. So both of them together can flow through here, through that resistor. So now that we have 0.5 on that resistor, or that we determine that we have 0.5 on I5, now we can determine also that voltage. Okay, so that voltage will be my 20 ohms times 0.5, which is equal to 10 volts. If you want, you can feel all these as you go, or you can wait till the end so you can feel all these values. The next one will be that at this point in time, I don't really know, to be honest with you, how much is my current here. But remember that I told you that the equivalent value for these two resistors, for that and that, the equivalent value for these two resistors was 4 ohms. So keeping that in mind, if I know that I have an equivalent value of 4 ohms between these two, and that is connected in series with R5, so the value of this voltage drops plus this voltage here has to be equal to 12 volts. Why? Simple enough. Look at this. Remember that we have a node here, a point, a connection point here, another connection point here. If I measure my voltage with a voltmeter between, okay, so I'm going to put it this way. If I measure my voltage between this point and this point, I'm getting between these 2 points a voltage which is equal to 12 volts. So now I want you to look at the circuit. Remember that I already told you that these two resistors is an equivalent resistor, which is equal to 4 ohms. Okay. Now, this 4 ohms is connected in series with what? With this 20 ohm resistor. And the sum, okay, that's important. The sum of this voltage here plus that voltage is going to be equal to the source, because this is connected between these 2 points. So it's getting a total of 12 volts. So if I already know that I have 10 volts here, then whatever is left is to make the 12 is going to be 2. So we have the 12 minus 10, that's going to be equal to 2 volts. So I have 2 volts here. And because they are in parallel, that means that E3 is equal to 2 volts. And that means that E4 is equal also to 2 volts. Now that we know the value for these voltages, we are going to find the current using Ohm's law. So we have R2 divided by 6 ohms. That's going to give me 0.33 amps, which is the amount of current going through that resistor. And then I have my same 2 volts divided by 12. So the I4 is going to be, 0.166. Remember that I told you before that I didn't know at the beginning how much current I have on these two? But whatever current I had to equal 0.5 at the end of the day. So you see that 0.33 plus 0.166 is equal to 0.5 amps. And now the whole circuit has been solved and we have been able to find all the values other than the value for power. But you know how to find power. It's going to be a matter now of saying like 1 times 12. This is going to be 12 watts. This is the easiest part to find power. Okay, so this one was 24 times 1 amp. It's going to be 24 watts total. And remember that power, the sum of all the powers in here, got to add up to 24. So I'll do that just to finish it, okay? So we have that 0.166 times 2. That's equal to 0.332 watts. So here we have that 2 times 0.33. This one here is equal to 0.66 watts. And then this other value here, 10 times 0.5, that's going to be equal to 5 watts. And the last one here, which is the 12 times 0.5, which is equal to 6 watts. Now, when we add up all these values, it has to add up to 24. So I got 12 plus 6 plus 5 plus 0.66 plus 0.332, and I'm getting exactly 23.992 watts. So that means that when I add all these numbers, when I add the value of all these wattages, it has to equal my total power. Well, this is it for today, guys, and I hope that this is going to help you out in getting immersed into combination circuits. Well, I'll see you next class, and I wish you very good luck this Friday for your second test. Have a good one.